This is AI Papers, a deep dive. We start where the work starts, the abstract, the method, the experiments, and we don't skip the parts that matter. Okay, let's do this.
A robot ran the same kind of job over and over, and the more tasks it finished, the better it got at brand new ones. No retraining, no new network, not a single weight changed. On tasks it had literally never seen before, it succeeded 31% of the time. The methods it beat scored 4, and those methods were allowed to retry and reason at test time. This one got a single attempt.
Quick heads up before we get into it. This is an AI-made explainer, both voices included.
So here's the promise. By the end of this, you'll understand how a robot can accumulate genuine engineering experience, the kind a senior programmer builds over years, and store all of it as plain, readable text. Not weights, text, and why that little detail might be the whole point.
And the part that should nag at you, it beat those baselines while getting less help than they did. One shot, no retries, on tasks outside its training. That shouldn't be the easier position to win from. So what's in its notebook that makes the difference?
The paper is called Aspire, out of NVIDIA and a big academic collaboration, posted at the very end of June 2026, so just days before we recorded this. And it starts from an observation that's a little embarrassing for the field.
The way we build robot software today, the agent solving its 100th task is no smarter than the agent solving its first. Every hard-won fix, the trick that a bottle tips over unless you grab it along its long axis, the workaround when the motion planner keeps refusing a path, all of it evaporates the second the task ends. Nothing carries forward.
Which is strange, because that's exactly the opposite of how human engineers work. And this matters beyond robotics. If experience can pile up as inspectable text instead of buried in network weights, you get skills you can read, edit, and hand to a completely different robot. Learning you can actually open up and look at.
Let me set the stage a little, because there's one assumption underneath everything. The robots here aren't running a single neural network that maps camera pixels straight to motor commands. Their behavior is a Python program. Actual code. Call a perception routine to find the red radio. Call a motion planner to go to this spot. Call a grasp routine to close the gripper. The robot's intelligence for a task is literally source code stitching together pre-built subroutines.
And that's the whole reason a debugging story is even possible. You can read a program. You can see which line broke and rewrite it, same as any other software. This approach has a name in the field, code as policy. The robot is running a program a coding agent wrote, not one big trained blob.
Right, and modern coding agents have gotten genuinely good at one specific rhythm. Write code, run it, read the error, find the bug, rewrite, repeat. The reason that loop works is rich feedback. A stack trace points you at the exact function and the exact reason it blew up.
And robotics never had that. That's the diagnosis at the heart of this paper. A robot coding agent traditionally learned one thing when something went wrong. The task failed. That's it. Imagine being a programmer and the only bug report you ever get is, your code is wrong. No line number, no error message, nothing.
So did the camera misread the object? Was the grasp unstable? Did the planner refuse a path? Was it a recovery problem downstream? The task failed can't tell you which. And a real robotics engineer faced with that would replay the run, inspect the camera overlays, look at the trajectories, figure out which subsystem broke, and then remember the fix for next time.
The cleanest way to see how Aspire fixes this is the story the paper itself opens with. And it's a good one. A robot trying to grab a red radio in a simulated household scene. Watch this trace on screen because it's the single most important picture in the paper. The robot finds the radio just fine. Perception returns a valid location, no problem there. But then it tries to approach the radio, and it fails. Tries again, fails. Again. Old-style feedback would just shrug and say, task failed. But Aspire's execution engine keeps a detailed record of every single call, so the agent can dig in. And it sees the navigation calls all returning the same thing, a planning error.
And here's where it gets specific. The agent goes into the return values, the logs, the frames, and it localizes the real cause. The spots it's picking to stand near the radio all fall within about 20 centimeters of the table edge, inside the motion planner's collision avoidance buffer. So the planner flat out refuses to find a path. The failure was never perception. It was never the grasp. The approach position itself was infeasible.
And the fix follows straight from the diagnosis. The agent doesn't fiddle with the camera prompt or the gripper. It writes a multi-angle approach, sample directions rotated around the object, try one side, rotate 45 degrees, 90, 180, until one of them lands in open space the planner will accept. It works. The robot reapproaches from a reachable side and completes the grasp.
But that's not the clever part. The clever part is what happens next.
The fix gets abstracted and saved into a library, written generally. If the planner keeps rejecting nearby goals inside its collision buffer, rotate your approach vector. Each angle puts the goal on a different side, and when one side's blocked, another is often open. A specific, painful failure becomes a reusable rule. That's the entire thesis in miniature.
And that's the senior engineer's notebook idea made literal. Picture someone who's spent years filling a notebook with hard-won rules. If the bottle tips, align the gripper to its long axis and close in 2 stages. Each entry was born from one specific disaster, but written generally enough to reuse. Aspire's library is that notebook, except the agent writes its own entries, and they're stored as plain, readable text.
So the system has 3 interlocking pieces, and the radio story just walked us through all 3. Tyler, you want to take the one that turns out to matter most?
The execution engine. This is the linchpin. And the paper frames the design problem really cleanly. Existing feedback is stuck in a bad trade-off. Give the agent too little evidence, and it can't see which component failed. Dump raw video on it, and it drowns, loses the causal thread. So the engine threads the needle. For every perception, planning, grasp, and motion call, it stores the inputs, the outputs, the return status, and snapshots of what the camera saw right before and after. It's the robot version of a stack trace, except part of the evidence is visual and needs interpreting.
And the payoff of that framing is one of the strongest results in the paper, but let me hold it for a minute so it lands properly. The second piece is the library itself, and the key design choice is that the skills are not a fixed menu written by humans. They're induced from validated repairs. When an actor fixes a failure, it files a structured report. Here's the failure mode, here's the fix, here's the pattern that might transfer. A coordinator audits it and only admits the genuinely reusable ones.
And the categories that emerge are all over the map. Localization tricks, perception prompts, grasping constraints, navigation recoveries, whole debugging workflows. Nobody prescribed that taxonomy up front. It grows out of what actually broke.
A couple of my favorites for texture. There's a bottle skill. Wine bottles tip over during a grasp because the gripper closes at some arbitrary angle and the bottle just rolls out. So the fix aligns the gripper to the bottle's long axis and closes in 2 stages. And a disambiguation skill. You say, the front bowl. The segmentation model hands back every bowl with no ordering, so the routine sorts them by position and picks the actual front one.
The third piece exists to cure a specific disease. Trace-guided debugging on its own can collapse into what the authors call local repair loops. The agent keeps patching the same doomed strategy, tweak, run, stuck fertilizing one sickly plant. So instead, they run evolutionary search over whole programs. Each round, propose a handful of genuinely different candidates, run them all, keep the best performers, and use those survivors, plus whatever still went wrong, to seed the next batch.
So it's less fix the one broken program and more breed a diverse crop and keep the strongest.
Exactly that. Except a plant breeder is blind and this isn't. Each new candidate is deliberately conditioned on the survivors and their leftover failure traces. It's a smart breeder, not nature. Diverse guesses, filter by what actually runs, feed the winners forward.
And one architectural note that keeps it sane: it runs many tasks in parallel, one coding agent per task, and those agents don't share their raw chat logs with each other. That would flood everyone's context. The only thing that transfers between them is distilled, the library entries. Each agent stays focused on its own task while quietly benefiting from everything the system has learned.
Now, before the results, there's a stretch worth slowing down for: how they measured this. It's not the flashy part, but it's what makes the 31 versus 4 number actually mean something, and it's the difference between a real result and a rigged demo.
Set it up because when I first read the protocol, I assumed Aspire was getting the easier deal. It gets to learn a whole library before the test. That sounds like an advantage.
It sounds like one, and it's actually the opposite. Every task instance is pinned by a random seed: object positions, distractors, starting state. Aspire learns on a small set of debug seeds, builds its library, and then gets evaluated on a larger, held-out set it's never touched, using one generated program per task. No test time retries, no do-overs. The main baseline, by contrast, gets to generate a fresh program for every single evaluation seed, with reasoning and retries at test time. So Aspire is playing in the harder regime and still winning.
And there's a rule I want people to hear, because it's what keeps the whole thing honest. The agent is banned from reading the simulator's ground truth. No peeking at true object coordinates, no reading the scene files to figure out geometry. The rule of thumb they use is lovely. If a real robot with a camera could do it, it's allowed. If it reads the physics engine's internal state, it's cheating.
It's poker where you have to read the table from what's visible, not by peeking at the deck. Because a skill you learned by peeking is worthless the second you sit down at a real table. That discipline is exactly what gives these skills a shot at transferring to reality. Hold on to that. It comes back.
Okay, the brain running all of this is a frozen frontier model, Claude Opus 4.6, with a context window around 1 million tokens. And I want to be precise about the word frozen. Its weights never change, not once. Everything the system learns happens in the text you feed it at runtime, not in its parameters.
Which reframes what learning even means here. Think of a brilliant consultant with no long-term memory who wakes up fresh for every job. It doesn't get smarter, you just hand it a better and better briefing packet before each task. All the accumulated experience lives in the packet. And that 1 million token window is what lets you stuff long execution traces plus a growing library of skills into a single prompt.
Which, flag it now, is also where the skeptic's knife goes in later. If all the intelligence is in the frozen model, how much is the notebook really doing? We'll get there.
We will. But first, the result I parked earlier. Here's the prediction. If the diagnosis is right, that the model was blind, not dumb, then just giving it eyes should move the needle harder than anything else you could add. And it does. On the perturbation benchmark, the base system, frozen model, a handful of example programs, no execution engine, no search, scores 14%. Add the execution engine alone, nothing else. It jumps to 62%. Then add evolutionary search on top, and the hard remaining tasks climb to 72%.
So the diagnostic trace is the giant lever, and search is the polish on the tail.
That's the shape of it. And the reading the authors give is the memorable one. The model was never dumb, it was blind. 14 to 62 just from letting it see what went wrong. Search cleans up the stubborn cases after that.
And once you've got the engine plus the library, the per-task swings get dramatic. On a 2-armed handover task, the success rate goes from 20% to 92%. On the household benchmark, That radio pickup we followed goes from 56% to 88%. And several Aspire results actually beat programs written by human experts.
Which is a real, wait, really moment. An agent debugging its own code, outprogramming the roboticists who built the environment. Not on everything, but on more than one task.
For contrast, the end-to-end vision language action models, the one big network maps pixels to actions approach, mostly collapse here. Under perturbation, a couple of them score essentially 0. Move the objects, rephrase the instruction, and the memorized mapping just shatters. That fragility is the whole gap code as policy is trying to exploit.
But none of that is the crown jewel. Bella, this next one is yours, and it's the result I'd actually rewind for.
So here's the setup, and I want you to feel why it's strange. Aspire builds its library by debugging short horizon tasks. Grab this, place that, single quick actions. Then they take that library and, with 0 additional debugging, point it at long horizon tasks the system has never seen. Multi-step chores, completely novel.
And your intuition is that short task experience shouldn't compose into long task competence. Different regime.
Right. And yet, 31% overall success versus 4% for the prior methods. And remember the asymmetry. Those prior methods were allowed test time reasoning and retries. Aspire was not. Experience distilled from short tasks composed into competence on longer tasks it had never encountered. The little debugging rules, how to approach, how to disambiguate, how to grasp, turn out to be the reusable atoms of the big tasks too.
And you can watch the compounding directly. There's a curve where they vary the library size. Empty library, 0 skills, about 5% zero-shot success. 25 skills, 14. 50, 21. 90 skills, about 30%. The gets better with experience claim made visible as a line that climbs with the size of the notebook.
That curve is the paper's thesis in one picture, and it's the best answer to your skeptic too. If the frozen model were doing all the work, an empty library and a full one would score the same. They don't. 5% versus 30.
It's the best answer. It's not the whole answer, and I want to come back to that. But first, the part that gestures at the real world.
The sim to real preview. This is small but striking. They took 3 skills discovered in a Franca arm simulation and handed them as text guidance to a completely different robot. A 2-armed station, different body, different API, running a different agent entirely. Codex on GPT 5.5.
The drawer task is the one to sit with. Without the skill, 0 successes out of 20, while burning an enormous token budget. With the sim-derived skill handed over as a note, 11 out of 20, at roughly a quarter of the tokens. A task that was flat-out unsolvable became solvable, purely from guidance grown cheaply in simulation.
And a soda can lift went from 13 out of 20 to 19, while cutting the token cost from around 62 million down to about 6.6 million, nearly 10 times cheaper. Skills discovered by Claude in Sim, helping Codex on real hardware. The knowledge transferred across robots and across different underlying models because it's just text.
And that only works because of the no peeking rule. If those skills had been learned by reading the simulator's guts, they'd be useless on a real drawer. That's the payoff of the poker discipline.
So the takeaway you can walk away with, even if you leave right now, give a robot programming agent a real debugger and a notebook it writes itself, and experience starts to compound as inspectable text across tasks, across robots. That's the shift.
And now the part this channel exists for. Because the numbers are strong, and I still think the framing oversells in 3 specific places. First, the compute. The headline is 1 program per task, no retries at evaluation. True, at eval time. But the authors are honest that building the library upstream is, in their words, compute intensive. many model calls and simulator rollouts per task in the debug and search loop. So one clean program at the end quietly hides an expensive apprenticeship. The fair comparison isn't eval time protocol, it's total compute, and that comparison isn't really made.
That's fair. The eval time discipline is real, but it's the tip of the iceberg.
Second, that clean climbing curve has ragged edges the aggregate smooths over. The zero-shot number is 31%, which also means roughly 2/3 of long-horizon tasks still fail. And per task, it's genuinely not monotonic. Some tasks get worse as the library grows. One goes from a 0.68 success rate at 50 skills down to 0.26 at 90. The library can go stale. Old entries get overspecific or redundant or actively misleading. The notebook that helps you can also start lying to you, and managing that is, by the author's own admission, unsolved.
That's the crack in the analogy I flagged earlier. A real engineer's notebook doesn't rot as it grows. This one can.
And third, the confound. Everything rides on a frozen frontier model with a 1,000,000 token window, and they concede they haven't tested whether weaker models can even sustain the debugging loop. The empty versus full library gap argues the notebook is doing real work. 5% to 30 is not nothing. But you can't cleanly separate how much is the library and how much is just Opus 4.6 being a phenomenal in-context reasoner. And the referee enforcing no peeking? It's itself an LLM audit. The transfer guarantee is only as good as that referee, and they don't quantify how often a violation slips through.
All of that lands, and I'll concede the honest scope. This is a research demonstration, not a product. The sim results are strong. The real robot evidence is 3 tasks and 1 robot body, explicitly framed as initial. So I won't call the drawer result a deployed capability.
But I'll give you the other side, because it's real. Even granting all of that, the 14 to 62 jump is a lesson that outlives this specific system. For agentic robot programming, the bottleneck wasn't the model's reasoning. It was that the model couldn't see what went wrong. Build it a good debugger, and it climbs on its own.
And that's the durable idea here. Bigger than Aspire, bigger than any one benchmark. The real result isn't the architecture. It's that experience can compound as readable text instead of network weights. Inspectable, editable, and portable from a simulation to a real robot, and even from one model to another. Learning you can open up and read.
So here's what I'd put to you. If robot skills can accumulate as plain text notes a coding agent writes, do you build the future of robot learning as a growing, human-readable library like this one, betting on inspectability and transfer? Or is that a clever detour, and the real path is still one big end-to-end network that learns controlled directly from data? 2 very different bets on where robot competence comes from. Drop where you land and why.
The full annotated version of this episode is on paperdive.ai. Every technical term, tap to define, with links to the related work grouped by theme, from the code as policy lineage to Voyager and the VLA baselines.
Quick housekeeping. This script was written by Anthropic's Claude Opus 4.8. Bella and I are both AI voices from 11 Labs, and the producer isn't affiliated with either company. The paper is Aspire, Agentic Skills Discovery for Robotics, posted at the end of June 2026, and we recorded this on July 2nd.
A robot that keeps a notebook and gets better the longer you leave it running. The trick was never a bigger brain. It was finally letting it read its own mistakes.